Are you ready to go?
Hello everyone.
Just
Good
give me a sec.
afternoon. My name is Shuli from Southeastern University. It is my great honor to be here to introduce our work. My presentation consists of four parts. The first part is background. First, I will give a brief introduction for next point of interest recommendation task. Next point of interest recommendation aims to predict the next point of interest that users are most likely to visit based on their historical trajectory. In general, this usually requires two steps. First, modeling the user's action preference from the historical trajectory. Then, use the preference to predict the next point of interest. Here, we focus on the stage 1. The preference modeling methods of many powerful models are generally divided into two types, such as modeling the overall preferences of users and modeling the long-term and short-term preferences of users. However, due to the neglect of the dynamics and the diversity of user preference, this leads to a preference representation with low expressiveness, especially in cases of sparse data. Therefore, modeling user preference with dynamics and diversity is the key of our work. So how to understand the dynamics and the diversity of user preference, we give our understanding. The dynamics emphasize that users' preference at each point of interest may vary slightly. So the preferences at the current location are most important for predicting the next location. Diversity indicates that a user's preference is composed of multiple latent preferences, and the most important latent preference determine where the user will visit next. So next, I will introduce the method we proposed. The framework of our model CLLP is shown in the picture. It consists of two key modules, sequence encoder and contrastive learning module. The sequence encoder is used to encode users' preference representations, and the contrastive learning module is used to optimize these preference representations. The sequence encoder also includes three components. The first one is an enhanced transform module. Here we replace the full attention in multi-hand attention with the local window attention, and append the spatial temporal layer after the multi-hand attention. Then we use the enhanced transformer to encode representation of each point of interest. The second module is an adaptive graph distillation module, which removes noise in representation and use collaborative signals from other user sequences. To be specific, first we design an adaptive graph construction layer to construct a weighted distillation graph. And then we propose a graph distillation operator to learn distinguishable information by removing similar information between neighbors. After distillation, we obtained more distinguishable representations. The next module is disentangled module. To capture users' latent preferences, we disentangle the representation of each point of interest into key latent preferences through explicit weights. And we use implicit weights to establish the connection with current preferences and the historical performance at all points of interest. Finally, we predict the next point of interest by using the mean latent preference of user at the current location. The last module is Contrastive Learning module. We design a data augmentation strategy based on sequence length and the correlation between points of interest to generate augmented sequences. Considering the similarity of users' local and global preferences, we obtained the local and global preference representation by encoding the augmented sequence to create positive and negative samples. and we use contrastive loss to optimize the latent preferences representation space. Then I will show the experimental results. Regarding the data size, we conduct experiments on two real-world datasets, Gavala and Foursquare. As for baselines, we use the following SOTA methods as the baselines in the experiments. In the experiments, we first compare the performance of all models. From the table, we can observe that our method outperforms all baselines on every metric, and compared with Foursquare dataset, we can see that the Gavala dataset exhibits higher data sparsity. However, the CLLP achieves more improvements on Gavala dataset. It implies that my model has a strong ability to handle sparsity data. To show the effects of many components in our model, we conduct an ablation study. The results show that each component contributes to the final results. Furthermore, when the enhanced transformer module is removed, the model's performance declines significantly. This indicates that the enhanced transformer has performed as expected. To demonstrate the robustness of CLLP against sparse and noisy data, we set up 3 groups of comparative experiments, focusing on augmentation strategies, sparse data, and noisy data. The result shows that compared to GetNext, our model performs better and is more robust to data variations. We also visualization results of latent preference representations generated by CLLP before and after the addition of the contrastive learning. As shown in the figure, our contrastive learning strategy makes the representations of same latent preferences to be close, and dissimilar latent preferences to be far apart. Finally, we come to the conclusion part. In this paper, we present a sequence encoder for modeling the dynamics and the diversity of user preference. Based on the obtained latent preferences, we use contrastive learning to learn more robust representations and elevate the data sparsity parabola. In the future, due to the flexible generation of large language models, we will explore the construction of effective fronts to expand the existing sparse dataset using the chain of thought. That's all. Thank you.